Conservation of linear momentum. Conservation of linear momentum. Linear momentum. Conservation of linear momentum. From Newton's law of motion. According to Newton's first law of motion, a body remains at rest. A body remains at rest are continuous to move. With a uniform velocity. So long as no external force is acting on it. According to Newton's second law of motion, the rate of change of linear momentum of a body is proportional to the force acting on it. Proof. Using Newton's first law of motion, if a particle of mass m is moving, moving with velocity vector v, its linear momentum p equal to mv. Linear momentum vector p equal to vector mv. When a force F is applied to it, its momentum change at the rate. When the force applied to it, its momentum changes at the rate. dp upon dt. Vector dp upon dt. So force F equal to dp vector dp upon dt equal to d momentum p equal to mv. The m vector v upon dt. Clearly when F equal to 0, then dp upon dt equal to 0 r. P equal to mv equal to a. Constant. A equal to constant. It is thus if no force act, the linear momentum is conserved. Thus Newton's first law of motion is only a special case of Newton's second law. Thus Newton's first law of motion Newton's first law of motion is only a special case of second law. Is only a special case of second law. Proof. Using Newton's second law of motion, now consider a system of two particles which are acted only by force of interaction like Coulomb's force or gravitational force, and no external force act on the system. Let F1 to be the force exerted by the first particle, and second particle. Force exerted by the first particle and second particle. on a second particle. F1 is the force exerted by the first particle on a second, known as action and F21. F21. That means force exerted by the second. Force exerted by the second and first. Force exerted by the second and first. Known as reaction. Then according to Newton's third law of motion, action and reaction being equal and opposite. By Newton's third law, action and reaction being equal and opposite. So F12 vector F12 equal to minus F21. According to Newton's second law of motion, vector F1 equal to dp2 upon dt, dm2 v2 upon dt equal to m2 dv2 upon dt, when m2 v2 and p2, when m2 v2 and p2 are the mass velocity and momentum of the second particle. Similarly F21 equal to dp1 upon dt equal to d upon dt m1 v1 equal to m1 dv1 upon dt, when m1, v1 and p1 are the mass, velocity and momentum of the first particle. F12 equal to minus F21. So F12 plus the value move of another side, F21 the sign sends minus by plus. F12 plus F21 equal to 0, or dp1 upon dt plus dp2 upon dt equal to 0, or d upon, wait just 1 minute, or d upon dt equal to p1 plus p2 equal to 0. Integrating, we have vector p1 plus vector p2 equal to a constant by integral rule. Constant are m1 v1 plus m2 v2 equal to a constant equal to constant. The quantity p1 plus p2 equal to m1 vector v1 plus m2 vector v2 represents the total linear momentum of the system. P1 plus P2 equal to m1 v1 plus m2 v2 represent the total linear momentum of the system. Hence we conclude that if Newton's second and third law of motion hold good, the total linear momentum of the system of two particles remains constant. The above law can be exerted to a system of three or more interacting particles. The law of conservation of linear momentum is therefore a basic law, and it is stated as under: the total linear momentum of a system. The total linear momentum, the total linear momentum of a system, the total linear momentum of a system of a particle free from the action of external forces and subjected only to their mutual mutual interaction remains constant. Mutual interaction remains constant. No matter how complicated the process are. No matter how complicated the forces are. The total linear momentum of a system of a particle free from the action of external forces and subjected only to their mutual interaction remains constant, no matter how complicated the forces are.